Fraser University, and the session is chaired by Professor Bapat. Please.
Yeah, I'm happy to welcome you all to this session. Our speaker is Professor BOJAN MOHAR. He received his PhD in mathematics in 1986 from University of Ljubljana in Slovenia. At present, he is at the Department of Mathematics, Simon Fraser University, where he holds the Canada Research Chair. His research areas are graph theory and combinatorics, theoretical computer science, and mathematics. He has authored more than 400 research publications and has more than 12,000 citations in Google Scholar. Some of the honors that he has received are as following. He's a fellow of the Royal Society of Canada. He's an AMS fellow.
Tell me question here over. क्या लगा? Question here over question.
A Siam fellow. Can you mute this audience?
Yeah.
He's a fellow of the Royal Society of Canada, an AMS fellow, Siam fellow, and he received the Euler Medal of Institute of Combinatorics and its Applications in 2010. So today he will speak on geodesic drawings of graphs and their limits. So I request Professor MOHAR to give his lecture.
Thank you very much for a nice introduction. And thank you for inviting me to this memorable conference. It's Ramanujan Centennial. We all are really glad to celebrate this influential mathematician from India. And today I will speak about combinatorial and kind of geometric topic, which does have little but not zero relationship to what Ramanujan did. So crossing numbers of graphs have applications in number theory, and so this would be a topic that might fits both main topics of this conference. So in this talk, I will say a few words on problems and areas as follows. So I will start with the most outstanding conjecture in crossing numbers. This is the Hill conjecture about what is the crossing number of the complete graph. I will divert to the 4-point problem of Sylvester. So that's kind of geometric, that's a topic that started geometric probability. And then I will also delve to geodesic drawings of graphs, not only in the plane, but on possibly different surfaces, and try to say what limits of such drawings would be. And then the major part in this would be also a good notion of what a random geodesic drawing on a surface would be. The last topic, Sylvester's crossing probabilities, I will probably skip out. So let me just start with defining what's a crossing number. Most people in graph theory would know, but there could be participants from other areas. So it just makes sense to define it rigorously. Usually we speak about crossing number in the plane, which means that we draw a graph in the plane with the minimum possible number of crossings. In this slide here, you see drawings of complete graphs K5 and K6. And K5 has one crossing. So this shows that the crossing number of K5 is at most 1. It could be 0 in principle, but we know that K5 is not a planar graph, so there must be at least one crossing. So this then says that the crossing number of K5 is 1. Similarly, you have K6 in the other picture and 3 crossings. So this shows that the crossing number is at most 3. And again, it's kind of an easy exercise to show that it cannot be smaller, so that 3 crossings are necessary. Now, about crossing numbers of complete graphs, Anthony Hill, he's an English painter who was interested in drawings of objects which looked like complete graphs. And then when you connect them, you need to draw the connections with over and under crossings. And he came to this conjecture, which sometimes is also called Harari-Hill-Guy conjecture, because Harari and Guy were also involved in the early developments of and popularization of this conjecture. It says that crossing number of Kn is roughly n to the 4 divided by 64. And there is a very precise formula with this integer parts. So you just say n over 2 times n minus 1 over 2 floor times n minus 2 over 2 and n minus 3 over 2. So that's the conjectured crossing number of the complete graph. For every n, there are known drawings which attain this bound, and none is known that would be having strictly fewer crossings. So this is a long-standing conjecture that we don't have a real idea how to prove. Even the asymptotic version, which I have here, that when n is large, this behaves like n to the 4 over 64 is open. So that's still open. I wrote here this conjecture in a different form by looking how many crossings per quadruple of points. So if you take 4 points, there will be 3/8 of a crossing in average. So that's the other way of expressing, and we'll come to this 3/8 a little bit later again. So that's the Hill conjecture. And similar to the Hill conjecture is the so-called Sylvester 4-point problem. So Sylvester asked about, about 150 years ago, what's the probability if you take 4 random points in the plane that these points will form a convex quadrangle? So this is very much related to drawings, because if you find if you take 4 points and they make a convex foregone, then if you draw the complete graph on these points, there will be a crossing. And if the 4 points don't make the convex foregone, there will be no crossing. So like this. So this is very much related to the crossing number of the complete graph. If you decide to draw the edges with straight lines. So Sylvester's problem got very different answers. Actually, already a year after this first 6 solutions came. And different well-known mathematicians answered the question by Sylvester. And as you can see, the answers they gave, this on the right, they were all different. That's something which rarely happens in mathematics. So 6 solutions to a problem and all of them with a different outcome. Well, the reason is that, of course, there is no natural definition of what random points in the plane would be. So each of these guys used a different notion. Like Woolhouse, he looked at the circles of radius 1 and then took 4 random points in there and got this nice little answer for the probability that the 4 random points form a convex foregone. And different guys use different, like Wilson used a triangle, and there the probability was 2/3. So this is this problem. It became apparent that it was ill-posed, and already a year after, Sylvester himself admitted that and asked about how to tackle this kind of problems. So, and that was basically the birth of geometric probability, which today it's an interesting field between combinatorics and the geometry and probability. The Sylvester problem is very much related to the rectilinear crossing number. So this is, again, we try to draw, let's say, the complete graph on endpoints, and then the drawing will not use edges drawn as curved lines, but we want them to be straight line segments. And then the minimum crossing number for this model is called the rectilinear crossing number. Scheinerman and Wilf actually proved that rectilinear crossing number is of a complete graph is very much related to the Sylvester's problem. In fact, they proved the following. So look at this definition of nu star. You take a large complete graph Kn. You take the rectilinear crossing number and you normalize with n choose 4. So when you do that, you get a number between it's between 0 and 1. And if you take the limit or the infimum, you get this nu star. So this nu star is it's not hard to show that there is a limit. So, and this would be called nu star. And Scheinerman and Wilf actually show that nu star is actually the worst case of these Sylvester probabilities. So you take all open sets in the plane. Usually it would be, you could say, maybe you can take such an open set here. And then you put 4 points in random and in this R, and then you ask what's the probability that they form a convex foregone. Now, if you go over all such open sets of area 1, say, you can normalize, then what you get is really in the infimum, you always get bigger than the rectilinear crossing number, because what you do is, so here is, let me try to convince you that the rectilinear crossing number is actually a lower bound for such a crossing probability Q of R. So if you take in this, if you take 4 random points here, the probability is that they will make a crossing once you do the random, once you do the rectilinear drawing, it's equal to Q of R. So that's the expected probability that you get a crossing. So if you, but expectation is linear. So the crossing number, the number of crossings is equal to the number of 4 tuples which do the crossing. So you can just look at the expectation. So the expectation of this crossing number of a D. So D would be, you take n random points here, and then you connect them with straight line segments. So crossing number of this drawing which you get is a random variable, and then the expectation is just equal to this Q of R times n choose 4. So that's just an easy proof, because crossing number of D is the sum of the indicator variables for every 4 tuple, where you so you take a variable x a b c d, which is 1 if a crossing and 0 if they don't cross. If there is no crossing with sorry, this is for the 4 points, for a set of 4 points. And then crossing number is just the sum of these indicator variables, and the expectation is linear. So so that's and this is the expectation of a single one of the events. So that's a very simple observation. Of course, you have to do the other way, and that's what Scheinerman and Wilf proved. So this, if you estimate this Q of R for every open set R, you get some bound. And also, if you get estimates on the rectilinear crossing number of the complete graph in the plane, then you also get bounds on this Sylvester, the infimum of this Sylvester probabilities. Today's state of the art here is that we have 2 rather close bounds, a lower bound and an upper bound. So for a lower bound, you just have some, well, for the upper bound, you just have some constructions which show the upper bound. And for the lower bound, there was a big breakthrough about 10 years, roughly 10 years ago, 8-10 years ago, that made this this number bigger than 3/8. So 3/8 is roughly 0.375, which is smaller than this. So it's it was a breakthrough to show that the rectilinear crossing number behaves in the limit for large graph much differently than just the usual crossing number of complete graphs. Now, we will extend this notion of rectilinear crossing number to a more general setup. So let's look at the Riemannian surface. Riemannian surface means that we have a notion of geodesics or local geodesics on the surface. We can say this is the shortest possible curve from point A to point B. So you have locally you have defined distance, and you can extend this to the whole surface via the notion of a Riemann surface. Let's assume also it's compact and everything is nice. So you may have questions. Sometimes surfaces wouldn't be so nice and so on, and maybe different, but it's not. So Riemann surface, it doesn't mean it's embedded in 3 space. So it's a surface. It could be defined locally. It's just by Riemannian atlases. Now, if we have a notion of a random point on a surface, and this notion can be defined by roughly as follows. So you can take a probability distribution mu. So I on the surface, so you have some probability distribution, 2-dimensional or maybe even degenerate, but let's say you have a 2-dimensional probability distribution mu on this surface, and then you can ask about the Sylvester probabilities again, Q of mu. So what is Q of mu? You take on your surface, let me say you have such a surface, and then you take 4 points, 4 random points on the surface, and then you join them with geodesics. So this will be shortest possible paths. And you ask whether these geodesics have a crossing or not. So it can be shown that there is at most one crossing. So, and then this would be called Q of mu would be, so the expected value for the crossing to occur if you choose 4 random points according to this distribution mu. For a while now, I will speak about a uniform distribution on the surface. So every point is equally likely, which means that you look at the small disk on the surface, and then a property that you choose a point inside, your random point inside this disk, is proportional to the area of this disk. So that would be the uniform distribution for a surface, but you can take any other, and this I will also stick with a little bit later. So I hope this is clear. Now, it's interesting, there is an ancient result, so more than 50 years ago, Moon proved the following. If you take a uniform distribution on the unit sphere in the 3 space, so the usual unit sphere, then this Sylvester 4-point probability is equal to 3/8. You remember the 3/8 we had before. So what does this show? This shows that the rectilinear crossing number on this unit sphere of Kn is actually equal to 3/8 and choose 4. Well, approximately, because of this, so I can say maybe I could say minus instead of plus here, because it's at least it is smaller than this or equal to this. But anyway, so it's very asymptotically, the 3/8 is the right answer if we consider. So it's the answer seems, just take a uniform, just take a random drawing, and then you will get something like a best possible drawing. I'm not sure that I will come to this, but I have a very, very good explanation for this, apart from studying the probabilities. So it's a very good explanation that this actually happens. Few years later, so that was already in 68, Richard Guy with 2 co-authors, Jenkins and Scher, published a paper on the crossing number of the complete graph on the torus. And what they did, they also looked at the random points on the torus. So they looked at a flat torus. So just a flat torus would be, you take the square in the plane, you identify opposite points, and you get the flat torus. And then you can compute what are the Sylvester probabilities that this flat torus. So let me just show you here. So Sylvester probability is that this flat torus, 4 random points, let's say like this 4, have a crossing. So these 4 don't have a crossing. Oops, I made the wrong one here, I guess. Let's say it's this one. So that would be 4 random points, and these 4 don't make a crossing, but you can compute what the probability is that you get a crossing. And what Guy and Jenkins and Scher did, they actually show that this probability is 5/18. And interestingly, this is smaller than 3/8. So this is strictly smaller. So that gives also an answer for the rectilinear crossing number of the complete graph in this torus, it's roughly smaller than 5/18 times n choose 4 by the same reasoning as I explained before. So this was the Guy et al. Result. Interestingly, they looked at this rectangle. They observed that if you take, instead of the square, you take any rectangle, and then they take the torus, the probabilities remain the same. So it wouldn't change if you take the rectangle model of the torus. But they somehow, it's not clear to me why they neglected the parallelogram. And it turns out that the parallelogram could do better result. So this is stated in this next theorem. So if you take a rhombus, so side lengths 1, and then this angle alpha, then the probability that 4 random points make a crossing strictly drops, which is amazing, an amazing observation. So it's, you know, for the planar case, if you take Sylvester probabilities in the plane, the rectangle or the rhombus or the rhomboids, they all have the same Sylvester probability because that's kind of affine transformations in the plane. But it's not the same when you flap this into the torus. You get different distances when you do this for the torus. So the best case for the torus is actually, which you could guess, it's when you have alpha equal to 60 degrees, so pi/3, and this gives Sylvester probability 22/81, and 22/21 is strictly smaller than 5/18. It's so today, I mean, this is as far as I know, this is best possible result, and it's a conjecture that this could be the crossing number asymptotically of the complete graph on the torus. But so far we have no evidence because apart from this, we don't have other examples. So this is only on a flat torus. I can prove that if you take a flat torus, it means Riemann surface with curvature 0 everywhere, then you get into one of these models, and this is the best possible. But maybe you have a different Riemannian metric on the torus, which gives you a better solution. That we don't know. Now, since we came from the planar crossing number to toroidal, you can generalize this to an arbitrary surface, and you can ask what happens on a surface of genus G. So you look at a crossing number on the surface of genus G, and you know, if your G is large, you can embed small complete graphs in that surface without any crossings. So it is different than the torus. But when n is getting large, you're still getting the number of crossings which are proportional to n/4. So you can again do this by looking at a Sylvester type question. So you can look at the probability distribution on some surface of genus G, and then you take a random drawing and ask what is the expected number of crossings, and you get these numbers which I define gamma G. So for fixed G, you can look at the limit when the size of the complete graph tends to infinity, and then normalize, of course, we then choose 4. So you get something like this Sylvester's 4-point probabilities on the surface. Of course, this depends on the surface you choose. As we had example on the torus, there were different outcomes. And so for gamma G, you can actually take the minimum, the infimum if you want, over all over all possible Riemannian matrix of genus G. So that would be a kind of possible question. What is this crossing rectilinear version of the, so because for here we always take geodesics for drawings, so that's why I call it rectilinear. And you see in my notation I put CR with the overline indicating that. Subscript G indicates for the genus G. So clearly you wouldn't object that once the genus gets bigger, this probabilities get smaller because you have higher variety of surfaces, and surface of genus G+1 somehow also contains surfaces of genus G in some sense. So this is an easy observation that this sequence of this crossing constants goes down. For a while, when I first thought about this, I thought, well, it goes down, and of course, it should be true. It should be true that the gamma G plus 1 is strictly smaller than gamma G. So this, at the moment, I cannot prove this, so this is a conjecture. But I guess this should be true. So we at least have the positive gap from gamma 1 is smaller than gamma 0. So we know that gamma 1 is smaller than gamma 0 just by the examples I showed you earlier. And I believe this is general. But now, where does this tend? What's the limit? Does it go to 0 or not? And this needed a little proof. Indeed, they go to 0. So the consequence of the part B of this theorem is that limit of gamma G when G goes to infinity is 0. How do we get that? Well, let me just give you a sketch of the proof for this part B. So for the proof, I take, so G is surface of genus G. I can embed a complete graph on K vertices. So draw it on the surface of genus G. And where K is roughly square root of K is roughly G squared. It is known that you can do this with G squared over 12 roughly, but so just put any constant here, so small constant. So you can draw a rather complete, sorry, G is K squared, so this would be G to the 1/2. So K would be roughly square root of G, and you can draw such a complete graph without crossings. Now you can draw it also geodesically. So you can draw it so that all edges are geodesic. So there is some metric on the surface where this drawing is geodesic. Let me just for convenience draw the surface of the double torus, but not a geodesic. So here I have my complete graph drawn. So this is my complete graph. Maybe it has 7 vertices or 8. So I draw. It's drawn with geodesics. So maybe and so on. So that just doesn't matter. And what I can do now, if I want a bigger graph, I take what I call a blow up. A blow up would be that I put a little disk around of each point, And then I put, instead of one vertex, I put P vertices in here. So I get P would be N over K. So I get, in total, I get K points. And then I join them with, so it also here. And then I join them with geodesics, which will actually be going very close to this drawing, the underlying drawing of the drawing of the small graph. And then you can just analyze what random points, just take random points in these small disks. How many crossings will they involve? And it turns out that the crossing number of this would be roughly n to the 4 times some bigger constant, or you can do also n choose 4 if you want, times a constant, and then times a constant divided by g to the 1/2. So that would be that would show that this geodesic crossing number is roughly it's smaller than, so when you normalize, it's smaller than constant divided by the square root of g. I must add that Cherokee and with several co-authors in '94 actually proved a stronger result. So he proved that if you take a normalized crossing number, they proved that if you take a normalized crossing number of Kn on a surface of genus G, it roughly behaves like constant times 1 over G, not 1 over G square root of G. So it is much smaller. It is not clear if that affects this, because his drawings may not be realized as the geodesic drawings. So who knows? There is an open question. So this is an open question still. Is it true that the 1 over G or 1 over the square root of G or something in between is the right answer? Now I'll go to, once you have a notion of random drawings, you can also ask about limits. So this is a very tightly related area. So let me just describe in a few words, the area of graph limits started by Latsilovas and his collaborators. So graph limits say the following. So you have a sequence of graphs, G1, G2, and so on, an infinite sequence. And then you can say this sequence converges to some object. So these objects in this theory are called graphons. And what are the graphons actually? What is this convergence? So let me define a topological definition of graph convergence. Basically, you take there is a metric, which is called a cut metric between graphs. So for any two graphs, you can define a distance, a cut distance. Well, it's a quasi distance, but let's not be too careful about that. So we can define a distance between two graphs. If they are same size or not the same size doesn't matter. And then so this set of all graphs now becomes a metric space. So you can look at graphs in this metric space and then see if these graphs somehow converge. So this would be graph G1 in this metric space, graph G2, and so on. Do they converge? And then you can say this is the limit. The limit actually need not be a graph. Might be a graphon. So, but there is a notion just using this. You say if the sequence of graphs is Cauchy in the metric sense, then it is convergent. And then you can take the completion of this metric space, and then so you get a complete metric space, and the elements are graphons. So this is the shortly about graph limits, about graphons. Now there is regularity lemma, which says the following, that if you take any graph or any graphon in this space, there is next to it, in a very, so for every epsilon, next to it, there is a small graph. Small, well, you need to do such weighted graphs. It's a weighted graph. Edges have weights between 0 and 1. And you extend the notions to the weighted graphs as well. And then this small weighted graph is in epsilon distance. So for every point in this space and every epsilon, there is a small weighted graph nearby. What do we mean by small? This is roughly just the regularity lemma. So the semi-ready regularity lemma says basically what I mentioned before, and I don't have time to go into technical details of the regularity lemma, but the lemma says that for every epsilon there is some number which bounds the number of vertices in this small weighted graph H, and then the weighted graph H you can let me do with 3 points. Maybe it has weight 1/2 here, and the weight 1 here, and then the weight 0 here. So this would be a weighted graph on 3 points. Of course, this is regularity lemma gives much bigger graphs, but regularity lemma says that this graph represents actually a graph where you put n over k, so k is 3 in my case, points like this. And then instead of this edge, you put a random graph with probability p equals 1/2. Here you put a random graph with probability p equals 1. Well, this is just a complete bipartite graph, and here nothing. So this is the way that every graph is represented by a small graph via regularity lemma, and then you can also in the graph limit setting, this has an epsilon distance from this graph. So my graph is not really purely random, but it's maybe quasi-random what it comes from a regularity lemma, but it's in epsilon distance from the given graph. There were geometric versions. I should mention just starting work of Alon Pach and others in 2005. So they prove geometric versions of regularity lemma. They are much better than, and very well suited for crossing number problems. I don't go into details, but let me just mention what I mean by a random drawing for such a small graph. So again, I have this graph, small graph H on 3 vertices that I had in the previous example. And then I have for every vertex, I define a probability distribution. So for vertex 1, I define probability distribution mu1, and for vertex 3, I define probability distribution mu3. And then I can define, so based on this little graph, which was 1/2 here and 1 here, and let's say, let me change to 1/3 now in this other case, I do the following. I choose, I take n points on the surface, and I choose first each point, whether it will be corresponding to first, second, or the third vertex here. So and then I take a mu1 random point. Next one, maybe it's in mu3, I take mu3 random point. And then again, I take another point, maybe it's a mu1 random and a mu2 random, and so on. I take n points randomly using this probability distributions. And this gives me points on the surface, and I can take a geodesic drawing, and I can ask what is the crossing number. And again, so I don't have time to go into details, but there are these Sylvester probabilities. Here you need to use the fact that if you choose 2 points in maybe this one was mu1 random and these two were mu2 random, what's the probability that the edges between the 4 edges between these points will make a crossing? So that's this probability, and then there is a probability that also if you choose 4 points in the same disk, what's the probability that they cross, and so on. So you have these probabilities which somehow determine basically the expected crossing number here, and you can use the same notion for the random. So this I call random blow up of such a graph, small graph H. So I think I'm almost done. I will take maybe a couple of more minutes if the organizers allow me to, and just say a few words. So this is so you can define random graphs and you can define limits of drawings via this geometric version of regularity lemma. And you can also ask what happens with the crossing graphs. So in the previous talk by Janos, he spoke about intersection graphs of lines of segments. And this is basically in that topic as well. So you take a drawing, you take the edges as the segments of your geometric segments, and then you ask, what's the intersection graph? So the vertices will be your edges in the drawing, and then they will be adjacent if they cross. So that's why from each drawing you get a crossing graph. And there are interesting things to observe. So one thing is if the sequence of drawings is geometrically convergent, then also the sequence of graphs are convergent. The intersection graphs are convergent. But the other way, it's not necessarily true. So I should also point out that we asked an interesting question. Just for geodesic drawings on the unit sphere, so this planar geodesic number diversion for the geodesic on the sphere. And what it turns out is that you can have a sequence of drawings of complete graphs which are convergent, but the crossing graphs, although they have the same number of edges because these are optimal, well, conjecturally optimal drawings, they have this Hill number of crossings, but the graphons they give, they are different. So it's interesting that they are different. Also, I should mention that you see, if you look at this normalized crossing number, so normalized crossing number of k, just do it kn. Instead of kn, you can do random graphs as well, or any other graphs via regularity lemma. So crossing number of kn normalized. This is a parameter. So theorem is this is a continuous. Continuous function. So what does this mean? It's continuous. It's continuous in this metric that I described for the graph limits, and this means that you can actually approximate well. And of course, about 5 years ago, Fox and Pach and Suk had a paper which actually proved that. So they showed that the rectilinear crossing number of the can be well approximated. So here, instead of complete graphs, you can just take any dense graphs. So any family of dense graphs via regularity lemma and the graph limits approach. So this is a continuous function. So you can because you can then you can approximate it well because you can use this approximation via regularity lemma. So there is a lot of open questions in this area. but I'm running out of time, and I would like just thank you for your attention.
Okay, are there any questions from the audience or comments? You may please ask by unmuting directly.
I cannot allow.
Yeah, so I don't see any questions. So I think we will conclude here by thanking the speaker for an interesting talk. Thank you very much.
So thank you, Boyan and Bapat. We'll come.
Okay, thank you very much. Bye-bye.
So we'll come to the next and the last plenary lecture of this conference by Tetali Prasad at 1845. And that will be followed immediately by the closing ceremony. And I would request, we are going to give some unexpected surprise announcements. So please join for the valediction also. So we will break for 30 minutes now.